Every function is a part of a larger family of functions that are all related somehow through the same features and characteristics. At the head of each of these families of functions, there is what's called a parent function, which is known to be the most simple or the most basic form of that family of functions. Now, two of these families of functions you've already dealt a lot with in detail in grades 9 and 10, linear and quadratic. The most basic linear function would be the equation y equals x, or using our new function notation, f of x equals x. This is a line that has a y-intercept of 0 and a slope of 1. And again, it's known to be the most basic form of the linear function. The most basic quadratic function you learned in grade 10 is y equals x squared. Using function notation, I've denoted this as function g, so g of x equals x squared. In grade 10, you use this basic form of the quadratic function in order to then compare it to more complex quadratic functions and use transformations in order to generate a graph. The parent function for the square root function, this is a new one that we're going to be looking at in the grade 11 course, is h of x is equal to the square root of x. And in this lesson, we're going to be looking at what does the graph of the square root function look like? What does the base or the parent graph, parent function graph look like for the square root function? And we're going to be talking about certain characteristics that the square root function has. There's two more parent functions that we're going to be looking at specifically in grade 11. So the next one is the reciprocal function, and this is the parent function is denoted by the equation j of x is equal to 1 over x. And again, we'll be looking at what does the graph of that parent function look like? What are the characteristics of the reciprocal function? Finally, we're going to look at the absolute value function, where the parent function equation is k of x is equal to the absolute value of x. Now, for the parent linear function, if we set up a table of values, we want to substitute in values of x and generate values for the function, or f of x. So let's say we use the values of x starting from -3 and going to +3. Now, if we substitute into the equation an x value of -3, well, if x is equal to -3, the other side of the equation must be the same. So f of x must also equal -3. Similarly, if we substitute an x value of -2, f of x must also be -2. And that pattern will continue. If we then graph each of these ordered pairs onto our grid, we're going to get the graph of f of x is equal to x. And this is something that you would have looked at in grade 9. So let's graph these coordinates: -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and 3, 3. So we get a line that goes through the origin like this. Right? That's the graph of f of x is equal to x. Again, this is what's known as the parent function for the family of linear functions. For quadratic functions, our parent function is g of x is equal to x squared. So again, if we generate a table of values, we want to substitute in the x values to get a value for the function. So if we substitute in a value of -3 for x, -3 squared, and remember the -3 would be in brackets, -3 squared would be +9, -2 squared is 4, -1 squared is 1, 0 squared, 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. If we plot all of these points on our grid, we will get the graph of the parent function for quadratic functions. And again, you've done this in grade 10, so we're going to go through this fairly quickly. -2 and 4, negative 1 and 1, 0, 0, 1, 1, 2, 4, and 3, 9. Okay? And we can draw in our parabola there. Don't forget to label your equation on the grid. And you also want to make sure the x and y axes are labeled as well. Okay, so there's our base graph or our parent function for quadratics. A couple of key features. Notice that for quadratic functions, we have either a maximum or a minimum point, depending on if the parabola is opening up or opening down. We also notice that for the parent function, the vertex is located at the point 0, 0, which also means that the one x-intercept is 0, 0, and the one y-intercept is also 0, 0. If we were to list the domain and range for this parent function, in set notation, for the domain, all x values are possible, and so we would say that x is an element of the set of real numbers. For the range, only y values that are greater than or equal to 0 are possible because this parent quadratic function is only located in the upper two quadrants. So we want y values that are real numbers such that y is greater than or equal to 0. Okay, so that's domain and range in set notation for the parent quadratic function. The parent function for square root functions is h of x is equal to the square root of x. Now this time we have to be careful when we pick x values because unlike with linear functions and quadratic functions, it's actually not possible to use all x values, i.e. the domain of x, the domain for the x values is not going to be all real numbers. There's a certain limitation that's put on this. And that's because if we look at this function, if we substitute an x value that is negative, we're actually not going to be able to do this calculation in terms of real numbers. And so we want to look at only x values that are greater than or equal to 0. So let's start with an x value of 0 and increase from there. Okay. Now let's substitute in those x values. So the square root of 0 is 0. The square root of 1 is 1. Square root of 2 would be root 2. Square root of 3, root 3. Some of these numbers aren't looking too nice. Square root of 4 is 2. Okay, so that one looks nice. The next x value that would have a nice square root number would be an x value of 9, and that square root would be 3. So what we might want to do is just look at graphing the coordinates that work out nicely as our points on the graph. So we're going to graph 0, 0, 1, 1, 4, 2, and 9, 3. Okay. 0, 0, 1, 1, 4, 2, and 9, 3. And we're going to draw in a nice smooth curve that connects each of those 4 points. Again, we want to label our equation on the grid, label the x and y axes as well. Now, if we were to state the domain and range for this parent square root function in set notation, for the domain, we know that our x values are restricted to only values that are greater than or equal to 0. So we want x values that are real numbers, and x is greater than or equal to 0. Those are the only x values that we are able to substitute into this equation to generate a y value. And in terms of the range, again, only y values that are greater than 0 are possible because it's not possible to take the square root of a number, square root of a positive number, and get a negative result. And so we want the y values that are real numbers and greater than or equal to 0. The parent function for the reciprocal function family is j of x is equal to 1 over x. It's called a reciprocal function because it is the reciprocal of the linear function y is equal to x. When we go to substitute in x values to get corresponding function values, what happens if we substitute in the value of 0 into this equation? Well, we would get 1 over 0. Is it possible to divide anything by 0? No. And so we actually get an answer that is undefined. 1 over 0. And so at an x value of 0, we can't get a y value that matches that x value. And I'm going to put a dotted line in on the graph where x is equal to 0 right now, because I know that I can't actually get a y value for x equals 0. So we'll come back to that in a minute. What happens when x is equal to 1? Okay, when x is equal to 1, we get 1 over 1, and so the function value is 1. So I know that the point 1, 1 is on this graph. What happens when I substitute in a value of x is negative 1? Okay, when x is negative 1, I'm going to get 1 over negative 1, which is negative 1. So I also know that the point negative 1 is on the graph. Okay. Next one, let's try what's an x value of 2. What's the function value? 1 over 2, and I'm just going to keep that as a fraction. So for an x value of 2, I have a y value of 1/2, right around here. What about an x value of negative 2? So 1 over negative 2, that's going to be negative 1/2. And so I've got a point at negative 2, negative 1/2, right about here. Okay. What about an x value of 3? I'm going to have a y value of 1 over 3, so 1/3. And that gives me a point here. Okay. What about an x value of negative 3? Well, similarly, that's going to give me a y value of negative 1/3. And so I get a point right about here. Okay? And you can notice actually that that pattern will continue. So if I have an x value of 4, I'm going to get a y value of 1/4, an x value of 5, I'm going to get 1/5. And my points are going to get closer and closer and closer to that x-axis. In fact, those points will never cross that x-axis or touch it, but will get infinitely closer and closer and closer to that x-axis as the x values increase. Okay? So I'm just going to put an arrow on the end of that curve to show that it continues in that pattern. Okay? But it's never actually going to touch a y value of 0 or the x-axis. So I'm going to put in a dotted line there as well, because I know I'm not going to ever have a point along that x-axis, because no matter what x value I put in here, I can never get a value of 0 here for y. Okay? And that's going to be true in the negative direction as well. Again, no matter what I put in for x, I'm never going to be able to get a y value of 0. Okay? These two lines are actually called asymptotes. And an asymptote is defined as being a line that the function approaches or gets closer to, but never actually touches or crosses. And that is what is true in this case. So this part of the function here is going to keep approaching and getting closer and closer and closer to that x-axis, but it's never actually going to touch or cross. Okay? Now, let's see what happens in this direction as x gets closer to 0. What happens between an x value of 0 and 1? Okay, so let's try an x value between 0 and 1. Let's say that x is 1/2. Okay. Well, if I substitute in an x value of 1/2, I'm going to have 1 over 1/2, which is the same as 1 divided by 1/2, which is equal to 1 times the reciprocal of 1/2, which is 2. So our y value here is actually 2. That gives me a point where x is positive 1/2 and y is equal to 2, which is right here. Okay? What happens if x is 1/3, which means x is getting even closer and closer to the y-axis now, closer and closer to 0. So if x is 1/3, I'm going to have 1 divided by 1/3. And for similar reasons as this, 1 divided by 1/3 will be the same as 1 times 3. So I get a y value of 3. So here is my next point. Okay? And again, this pattern is going to continue. So as my x values get closer and closer to 0, my y values are going to increase and get closer and closer and closer. This function gets closer and closer and closer to that y-axis. Okay? And again, that's the definition of this asymptote here. So the asymptote is at the y-axis and at the x-axis. So this right here is part of my function. In the negative direction, it's actually going to follow the same pattern. So if x is negative 1/2, okay, you can check the algebra on this, but for the same reasons as this first calculation we did here, if I put in negative 1/2, 1 divided by negative 1/2 is going to work out to negative 2. And so negative 1/2, negative 2, that gives me a point here. And again, that pattern will continue, and I will have points getting closer and closer and closer to the y-axis, but never touching or crossing the y-axis. Okay? And so we get this function here, and I'm going to draw it over it in another color so you can see it more clearly. And this function here is the parent function for reciprocal functions. And so you can imagine taking this parent function, and just like with quadratic functions in grade 10, you can apply transformations to this parent reciprocal function and see what happens when you apply a vertical stretch or compression or horizontal translation or vertical translation or reflection. Looking at the domain and range for this function, okay, again in set notation, and you can try doing some of these later in interval notation as well. In set notation, all x values are possible to use in this function except for an x value of 0, and that's because we can't divide any number by 0. And so what we want is all x values that are real numbers except for x equals 0. So I'm going to say x cannot equal 0. Anything else is okay, but not x is equal to 0. And similarly for the range, any y value is possible except for that y value of 0 because we have that asymptote at the x-axis. So y can be all real numbers except for y is equal to 0. So we're just going to say y cannot equal 0. The parent function for absolute value functions is k of x is equal to the absolute value of x. Now, these absolute value symbols indicate that we're going to take the positive number of whatever is inside those absolute value symbols. Okay? So let's say that we have an x value of 1. Okay? So if we want the absolute value of 1, we're going to take the positive number of whatever's inside. Well, that number is already positive, and so the answer is just going to be 1. So let's say we have an x value of negative 1. So negative 1 inside the absolute value symbols. We want to take the positive number of whatever's inside. So instead of negative 1, that's going to be positive 1. Okay? Similarly, if we have an x value of 2, the function value is going to be 2 because that's the positive number. And if we have an x value of negative 2, again, we're going to take the positive number, so it's going to be 2. Okay? For an x value of 0, 0 is neither negative nor positive. That's just going to be 0. That's just going to be 0. So if we start plotting these points, the point 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Right? And if you think about it, if we have an x value of 3, that's going to be positive 3. X value of 4, that's going to be positive 4. And that pattern is going to continue in both of these directions. Okay. So here's our parent function for absolute value. So again, let's label the equation on the graph and label the x and y axis. Okay. If we look at domain and range for this parent function, the domain, any x value is possible. And so we're going to write that as x is an element of real numbers, and then close that curly bracket. For the range, any y value is possible as long as it is greater than or equal to 0. And so we want y can be any real number that is greater than or equal to 0.